Hello everybody, I'm Nick, the Raging Cajun from the University of Louisiana. And this video is the second in a series that covers the EPS system on our K4 project. This video is done for reference only, and my challenge to everybody looking at it is to see if I got the right ideas, and if I didn't, straighten me out, or if not, improve this thing. So what you're looking at is 10 of these little solar panels that we plan to fly and test, and they're on a stand out there in the sun. But here's the data collected from them. And of course you'll see a curve, and on the x-axis is voltage, and on the primary y-axis is power, and on the secondary axis in red is the current. Now, of course, what's important is what we call the knee, the power knee, and that's this blue curve. So as we increase the load, aka reduce the load resistance, the power delivered to the load goes up. And if we keep decreasing that resistance, ultimately this thing will try to consume more power than the solar panel can deliver, and the actual output of the power falls off. Hence, we want to find the peak, or what we want to do is design what we call a peak power tracker. Now, there's several ways to do this, but the way I'm explaining today is we call a perturb and observe. So what we're going to do is perturb it, observe it, see if it produced more power. And if it did, we'll keep perturbing it in that same direction. If not, we'll reverse it. So as we observe and perturb, we will walk across this peak, and the hope is that we will generate the maximum power we can get out of this solar panel. So now let me shift gears and bring you up to one way we can do this. And this is a simplified peak power tracker. And let me just go through it with you. So we have the solar power panels input here on the left, and it comes down to a buck-down converter. So if we start at volts, and ultimately we want to charge a battery, which is 4 volts, we could use a buck-down converter. And the one I picked, let me see if I can pick this up. The one I picked is a Texas Instrument TPS 6301. There's several in this series. So in comes solar panel voltage. We'll step it down to charge our batteries and go out to our load. So we come through a shunt resistor, which just measures the voltage drop across this thing. In our scheme, it's about a 0.05 ohm resistor. This device is an I2C device that reports back to our processor on the I2C bus both the voltage and current. Now, the way this device works is the output voltage is set by the ratio of this resistor, R2 and R3. Now, if we're clever enough, we can make, instead of this being a fixed resistor, this could be a resistor driven by an I2C bus. So by changing the value of R3, we can essentially change the value of the voltage over here to the load. So as we increase the output voltage on this step-down converter, we will deliver more and more power to the load. At some point, we will exceed the requirement of the load, which the solar cell can't produce, and we will actually make less power delivered to the load. So that's why we call it observe and perturb. Now, here comes the third piece of this thing, and actually turns out to be the most complicated. If I can bring it up. This is a battery charge curve. It's complicated. And the link between all three devices are complicated and may take some thinking. And unfortunately, because I'm not a good explainer, you may need to do some research on your own. But let me talk about this curve. So on the major x-axis is cell voltage, and on the secondary on the secondary x-axis is percentage of charge in the battery. Now it turns out that the charge discharge, we can optimize the number of charge discharge cycles by not charging the battery fully charged and not discharging it fully discharged. So if we operate in this range, say 80 to 30%, we get several thousand charge discharge cycles. So how can we limit the amount of energy flowing into the battery? Well, it's simple. All we do is at this voltage point right here, say if we don't exceed 4 volts charging, we will never put more than about 80% of the energy in the battery. So at some point, if we take too much energy out, we'll have to dump the load. So what the strategy is that we will gradually increase the voltage going to the battery, and because the low voltage would go up, we will have a further buck-down converter past this thing. So we will observe and perturb. We will try to increase the current going, the energy going to the load, aka the battery, until the solar panel can no longer deliver it. If we increase the load beyond what the solar panel can deliver, the battery will then contribute energy to the load. It's complicated. But it's important that we not let the charge voltage get above, say, 3.9 volts per cell, and we don't want it to drop below about 3.3 volts per cell. So that's what we're about. Now let's go back and review. Let's go back and kind of review the schematic once more. Remember that the output voltage going to the battery and the load is a function of the ratio of this resistor. So we can gradually increase the voltage going to the battery and the load until the power stops increasing. At that point, we'll back down and we'll dither about the maximum peak power tracker. All right. This is my ideas. Your challenge is to go make sure I got it right, and if you think of ways to improve it, let me know. So long.